Now I'd like to introduce you to today's speaker. Today we will be hearing from Kevin Trumpy, the Senior Product Manager from Standard Precision GNSS Product Center Positioning at u-blox. In this role, Kevin is responsible for the development of consumer industrial tracking products with a specific focus on wearables. At this time, I'll turn the presentation over to Kevin. Kevin, take it away.
Thank you, Jessie. Hello everyone. Today I would like to introduce you to one of our latest GNSS receivers, the MIA-M10. First, I would like to go over the applications MIA has specifically been designed for. Then I will cover some of the product highlights as well as the two product variants. And then I will go into some of the performance metrics that MIA achieves. And at the end, I will be covering a customer case or success story for you to see how MIA actually works in a real application. And at the end, I'm happy to answer the questions you have. So let's dive right into it. The MIA-M10 is currently the smallest GNSS receiver on the market. It brings very good battery life. So compared to the previous generations, we double the battery life, and we also achieve accurate positioning in various terrains where the GNSS signals might be weaker or obstructed by buildings. Let's go into the target applications. MIA-M10 has been designed for size-constrained, battery-powered tracking devices. As you can see, it has been designed or can be used for people trackers, animal trackers, asset trackers, but also drones, biocomputers, and cameras. Those are just some of the examples where MIA has been designed for, because all of those devices are battery powered and would like to achieve as long as possible power autonomy, but also provide an accurate as possible position. Now let's go into the first poll questions we have for you. The question is, what application are you intending to use the MIA-M10 for? Is it A, a pet tracker, B, asset tracker, C, people tracker, drone, biocomputer camera, AR, VR glasses, or if you intend to use the MIA for any other type of applications, please type in the answer. Okay. I think you might have clicked or answered the question. Let's continue. So what challenges do most of those applications face? It's the miniature design. So you have very constrained space to design your electronics into the device. And because the device is so small, the battery is also going to be small in your device. The third constraint is that because the device is small, you can only fit also a small antenna, which is limited to receive signals and basically transmit those signals weaker. So you cannot take full advantage of a well-designed antenna in a small device like this pet tracker you see in the image. So what have we done with the MIA-M10? Here's some of the key highlights to show you how we address those challenges. First of all, we designed the MIA to be as small as possible. We say it's as small as a chip design, but it brings the benefits of a module. It also has or features 65% less power compared to previous generations. And we also introduced very good power save modes to save even more power and increase the battery autonomy for your device. We also introduced to track a fourth satellite constellation with the M10 series. This enables you to have more satellites available for you to have or generate a position. We also introduced a new feature to compensate for weak signals as well, especially for situations where you might face a challenging environment with weaker signals. Here I wanted to give you an overview and compare MIA to our other products in our portfolio, and you can see how small MIA is. What I also wanted to point out is that the MIA is also very thin. So if you have an application that is also height constrained, MIA is a perfect fit because it's only 1 millimeter in sea height. What are some of the benefits of the MIA that is a SIP module? Because it's a module, it's highly integrated, and it means all the critical components are integrated and you don't have to manage those additional components by yourself. But it also results into a lot smaller footprint. Because all the RF components, such as the SAW and LNA filter, are already integrated into the MIA, it also results into less design effort and testing complexity. In a later slide, I will show you the comparison between a chip design versus a design based on the MIA. And because all the components are already integrated in the MIA, it reduces the effort for designing, finding suppliers for additional components, and in the end, you will be much faster to market with your product. Let's compare a chip design versus the MIA, a design with the MIA. On the left-hand side, you see the chip-based design, where you see that all the components here highlighted in orange, the LNA, the SAW, for maximum sensitivity and maximum interference. Those are components that you typically need when you design a GNSS receiver. You also see that we integrated a DC-DC converter to make this module as power efficient as possible. And in addition to that, you also need an oscillator as well that is also part of the MIA product. So you see on the right hand side, MIA doesn't need any external components. You only need to attach an antenna and the power supply, and to exchange or to control the MIA, there is either an SPI or a UART interface that can be used. Here I go into the details of how much smaller a design would be if you base it on the MIA-M10. It's up to 30% smaller. As you can see, with a chip design, you would place those additional components around the chip, which makes the footprint a lot larger. Let's go into the two MIA product variants, the MIA-M10Q and the MIA-M10C. The MIA-M10Q has, as I pointed out before, all the components integrated, and it is very well suited if you have a device that only needs a small external antenna to work. The MIA-M10C is a little bit a stripped down version of the MIA-M10Q. It is not power optimized and it doesn't integrate the RF components such as the LNA and SAW. This design has been optimized for an active antenna. That's why we have left out those components in the MIA-M10C design. What you also can see, the RTC is not integrated in the MIA. It's an optional component. It's not necessary for the GNSS to work. It would be helpful to have it when you go into shutdown your GNSS receiver and you bring it up, and in a startup sequence, the RTC would have maintained the real-time clock, which helps you to synchronize with the GNSS signal to get to a first position a little bit faster. Here again, a little bit more detail, the differences between the MIA-M10Q and the MIA-M10C. The MIA-M10Q features a temperature-controlled oscillator. This is especially helpful to be faster to synchronize with GNSS satellites. We also have the embedded LNA for the best sensitivity. We integrated a SAW and an LTE band 13-notch filter against RF interference impact, and this module can be operated with 1.8 or 3 volts supply voltage. On the other hand, MIA-M10C, it has the same pinout as the MIA-M10Q. This one features a crystal oscillator, which is okay if you have an active antenna, you have stronger signals. So with this design approach, you wouldn't need a temperature control oscillator for the same performance. And as you would have an active antenna, you also would not need a SAW and LNA components in this design. The MIA-M10C only operates on 1.8 volt supply voltage. Here another side-by-side view of those two product variants. One features the DC-DC for lowest power consumption. The Q also has a wider supply voltage range, as you can see. Then you have the different types of oscillator between the two variants. We have the RF components integrated in the Q, optimized for passive antenna, and yeah, that covers those two product variants. Here a more an overview showing the block diagrams, so you can see how this would look like on a schematic or on a block diagram. You see with the MIA-M10Q, everything is integrated in the green box in the SIP module. You add the antenna, you're done. Here with the MIA-M10C, you have the maximum flexibility where you would add an external antenna combined with an LNA, or if this is combined in one package, it would be called active antenna. Let's go over some of the performance characteristics of the module. As I mentioned before, when we compare the M10 series compared to our previous generation module, which was based on the M8, the MIA-M10 now uses 65% less power consumption. We have additional modes called power save modes where you can save an additional 50% power. And I will go over those power save modes in a little bit more detail. We know there are different applications with different needs in terms of update rate and power consumption. For example, here I have a sport bike indicated on the left. Here you would need a much higher update rate, typically 1 Hertz, which means once a second you get a new position. But if you go on the other side of the spectrum, like an asset tracker, you would maybe need a position every hour. So this means we would need different modes to serve different applications. And maybe for a person or a kid, you might track them every 5 minutes, 10 minutes. That might be frequent enough. So we have different power save modes. Here I start with the cyclic tracking mode. This is typically used for modes where you would have an update every second. So here we would just save power, but maybe compromise a little bit on the accuracy. But in open sky scenario, you wouldn't notice a difference. Then we have an on-off power save mode where the receiver starts up, acquires satellite signals and calculates a position fix and then shuts down again, waits 1 minute or 5 minutes and repeats the sequence. We also have another power save mode or another operational mode called cloud locate. Here the GNSS receiver would start up, collect or record the signals that the receiver can see and would send this set of parameters or to the cloud, where then the position would be calculated in the cloud and not on the receiver itself. So we would basically move this power hungry calculation from the GNSS receiver to the cloud, and we can save more power with this fashion. What's worth noting here, the position then would only be known of the device in the cloud and not the receiver itself. Let's go over some of the power consumption figures for both of these product variants. We have on the left the MIA-M10Q with the temperature controlled oscillator, the DC-DC converter. When we configure this GNSS receivers to track 2 constellations, we would consume around 25 milliwatts. If you configure to track more constellations, 3 or 4, we would consume more, 30 milliwatts, respectively 32. And as I indicate in the brackets is the power save mode, how much power you would consume there. So for 2 constellations, it would be 15 milliwatts, and with 3, 16 milliwatts. The power save mode is not supported with 4 GNSS constellations. Going to the MIA-M10C, the power consumption figures are pretty similar, but MIA-M10C is not optimized for the lowest power consumption, as you can see. What also worth noting here is that the power save mode indicated here, the power figures are based on the cyclic tracking power save mode, so 1 position every second. What I also wanted to share with you, maybe for applications that have a very demanding update rate, we have 2 options here. So the MIA can be, as default, is configured to have an update rate of about 10 Hertz with tracking 2 constellations, as you can see with GPS and Galileo. But it can also be switched in a more high performance mode where we can achieve an update rate of up to 25 Hertz in a single constellation mode. Or let's say if you track 2 constellations, we can go up to 20 Hertz in GPS and Galileo mode. Now, what I wanted to bring to your attention is more of the startup sequence of a GNSS receiver. So typically, when you start up the receiver, you wait typically in a good conditions about 30 seconds to get your first position. And if the conditions are suboptimal or adverse, this can take minutes or hours, or it takes just longer. Because you would need a steady, good connection to the satellites. And the longer you search or connect to satellites, the more power hungry this becomes. And also, the performance maybe takes longer to acquire satellite signals. You might only connect to a handful of satellites, where if you had good conditions, you could connect to more satellites. So let's go through the startup sequence of a GNSS receiver. It's called cold start, so you don't have any prior information of any GNSS satellite. So first you would start up, search and synchronize with the satellites, and once you found satellites, you would then receive and decode ephemeris. Those are orbital data of the satellites. And after, in good conditions, about 30 seconds, you downloaded this ephemeris data, you can start the tracking. So you would be able to calculate positions. And as you can see in the second picture, if the signals are poor from the GNSS, maybe obstructed buildings, maybe you are between buildings or in a forest where the signals get attenuated, then it becomes difficult to come to a first position. But we can help with that. If you were to feed the receiver with this orbital data in advance before you or right after the startup, you don't need to connect to the GNSS satellites. You would have this information available already, and you can start tracking or calculate the position immediately. And on the next slide, I wanted to show you how big of a difference this makes. So we have here a cold start. Let's look at the column GPS and Galileo. In a normal, good condition case, we would have 28 seconds, as I said, around 30 seconds. But with assistance data, or this orbital information fed into the receiver, you can push that down to about 2 seconds. We also have a mode, it's called autonomous, where once you first acquired a fix, you would then retain this orbital data in the receiver, and on your next startup, you would still remember this orbital data and take this to your advantage. But the longer you wait for your next startup, you will have a decay in this orbital information, so it becomes less accurate over time. So it will take you longer to connect to the satellites. So what are the benefits of this aiding the orbital information to the receiver? Obviously, as we've seen, you can reduce the time to first position fix from 30 seconds down to 2 seconds. This also helps you in challenging conditions. You could connect to more satellites, which in turn result into a better accuracy. And obviously, if you only need to spend 2 seconds for the first positions, you save a lot of power as well. What I also wanted to highlight or bring to your attention is the benefits of tracking 4 satellites compared to 3 with our previous generation. So as you can see on the picture, sometimes you as a person are between buildings or in a forest and don't have direct line of sight to a satellite, which typically attenuates the GNSS signal, making it more difficult for you to calculate or to have a position. Therefore, it comes in very handy to track in additional constellations to increase your chances of having a direct line of sight to the GNSS satellite. So here I wanted to show you the difference between 3 constellations and 4 constellations in an urban environment. And you can see here, green is the truth, and I would maybe you pay attention first to number 1 in the right image. There we don't have any obstructions of the sky, and as you can see, 3 constellations versus 4 constellations doesn't make a big difference here. But as you move into a more dense urban environment, you can see that the blue track is closer to the green track, and which means the 4th satellite constellation helps you to become more accurate in this type of scenario, in number 2. Let's move on. I would like to explain you our new feature called Super S technology. Here I have to highlight 2 points. One is that we made our GNSS receiver silicon more sensitive. And the second point is that we improved our firmware in such a way to compensate for weak signals. So let's go through the first point. As you can see, for some of the constellations, we improved the sensitivity by about 3 dB. It's for the Baidu, the Galileo, and the GLONASS. 3 dB means about twice sensitive as before, so a big difference. This significantly lowers the time to your first position. On the other hand, we also improved the firmware where we before disregarded signals that would fall under a certain threshold, but now we take those signals into account and we can actually achieve a better position accuracy. So you can see the track in red before without the compensation. Now with compensation, we have a much improved position track, which typically is better than 25% accurate. Here I wanted to show you also how we compare to competition in a scenario, in a pet tracking scenario. And you can see here in green, again, the truth. We are, with our MIA-M10, we are tracking 3 satellite constellations versus a competitor with 2 satellite constellations here. And you can see in red, the MIA tracks the green truth very well. And I have to say, this is with a very good antenna. And our competitors here, they don't achieve such an accurate position as we do, as you can see. They are drifting away and are much further away from the truth. When you compare the power consumption as well, here in this scenario, we consumed on average 28 milliwatts versus the competition 35. And on a statistical view regarding position accuracy, you can see we are minimum twice as accurate as the competition. But now I want to show you how does this compare in a scenario where you have a small passive antenna. As you can see, again, green is the truth and red is the MIA-M10Q. So this is maybe a very challenging scenario with this small antenna. And as you can see, the competition has a hard time to stay on track with the truth, where the MIA-M10Q still can follow the truth very well. And as we can see, now the difference in position accuracy between the MIA and the competition is even bigger than before. We have the best position accuracy, the best position availability because we track more constellations, and we have the lowest power consumption as well. Now, let's get to our second poll question. What is the most important in your application? Is it you can have select multiple answers here from A, power consumption, the small footprint of the GNSS position accuracy, spoofing and jamming resistance, or is it the low effort for integrating a GNSS solution? Okay, let's continue. Here I would like to share with you one of our customer cases with NoFence. NoFence is a company that came out with a device for animal tracking so that they can track the animal, but at the same time, it doesn't require the farmer anymore to put up any fences. The fence can now be virtual. So they designed a collar for the animal that has a GNSS receiver integrated as well as a cellular module. So how this looks like here, from a bird's view, you can see the virtual fence in white, in the white line. As soon as an animal comes close to this virtual fence, the collar would emit a sound and signal that the animal is close to the fence. And at some point, the animal would retract from the virtual fence and knows, okay, I'm coming close to the border here. And on the right-hand side, you can see this designed collar. So if it would come even closer to the fence, it also would emit a slight electrical shock as well. So as I mentioned before, this collar has a cellular module in it, so it's connected to the cloud, and it is also connected to the GNSS satellites with our MIA GNSS receiver integrated. How this works is the farmer would have an app on a phone where he can define the virtual fence, and this information would then be transmitted to the collar of the animal, so it's programmed to signal or emit the sound at the right moment. Why has NoFence decided to use the MIA for their design? They saw the benefits of this highly integrated module. They were able to quickly integrate it because we also have very good evaluation tools as well. And with all those benefits, they were very quick to design the first prototypes and evaluate this product and come to market as quick as possible. And obviously, low power consumption was a key factor in deciding to integrate the MIA. So a high power autonomy was key for this application, which the MIA was exactly designed for. Here I want to go over the MIA product availability. So the Q is available already in Q. As of now, it has been available for some months, and the MIA-M10C will become available in Q3 of this year. But both of those modules can be evaluated with our EVKs, the EVK-M101 and the EVK-M101C for the C variant. Both EVKs are available already. Let's go over a quick summary. So the MIA is a very small GNSS receiver, the smallest you can find on the market. It has a very low power consumption, allowing you a very high or long power autonomy. It doesn't need any external components. It consumes, when you track 2 satellites, less than 25 milliwatts, and it has excellent performance in any scenario where it's obstructed with high buildings, or maybe the signals are attenuated by a forest. We still can provide a very good position accuracy. For more information about the product or any other helpful tips and tricks, please visit our website. We have more information about our M10 products. We have a white paper that outlines more about how to operate your device to get as low power as possible. We also have a blog and more insights to find how to achieve your goals or maybe enable new applications. I also want to point out that we have excellent evaluation tools. We have the IoT Explorer Kit. It has features short range, GNSS, cellular, everything in one module, so you can get up to speed very quickly. We also have u-blox library, where we have code that is already pre-developed for you to really get up to speed very quickly. As I mentioned before, the EVK-M101, it's available for you to evaluate the MIA. And we also have a good tool where you can see and evaluate position, power consumption with the U-Center too. Now I'm at the end of the presentation. Thank you. Thank you for listening.